All right, so we're going to start chapter 5, which is on exponential functions. Okay, so first I want to just compare these two expressions, x squared and 2 to the x. Okay, in each case, there's a base and there's an exponent. Okay, in the first one, x squared, the exponent is a 2, and the base is an x. In the second example, okay, 2 to the x, your exponent is an x, and your base is a 2. Basically, what we're looking at here is we're kind of transitioning from having numbers as our exponents, okay, which we had with polynomials, to having variables as our exponents. Okay, so we've already studied the kind of problem where your variable is in the base and your exponent is a non-negative integer. Okay, that's a polynomial. X squared, 5x to the 5th, things like that. Those are polynomials. Okay, but when you put the variable up as your exponent and you keep the base as a positive real number, any number you want except 1, that's when you have an exponential function. Okay, exponential functions are used to model lots of kinds of situations. If you had, let's say, a bacteria that doubled how many bacteria there were every hour, that's an exponential problem. Okay, if you had, say, something that was radioactive and it had a half-life, okay, we can model, for example, half-life basically tells you from, if you've taken chemistry or physics, how much time has to go by for half of the material you have to disappear. That's also an exponential function. Okay, so we'll look at some other examples. Another one would be like a population of a city. Let's say the population of a city continued to grow at 2% every year. That would be an exponentially growing city. Okay, any questions about kind of the types of problems you might use it for? Yeah?
Basically things that increase or decrease really quickly.
Yes. Things that increase or decrease very, very quickly. Yep. Okay, so in this case, f of x here is an exponential function. The domain of an exponential function is negative infinity to infinity. Okay, x can be anything you want. But the base has to be a positive real number. And the only positive real number it can't be is 1. Okay, think about what would happen if you plug in 1 for the base and you raise that to a power. If you raise 1 to a power, what number do you always get? Yeah.
1.
Yeah, we get 1. So if you have 1 as the base, it wouldn't be growing or decaying. It would always just stay 1. Okay, so here's some examples of exponential functions. 10 to the x, 4 to the v, pi to the x. They all fit the definition that they need to be an exponential function. Base is a positive real number other than 1. And you have your variable up in the exponent. Okay, these are all things that are not exponential functions. Okay, x cubed, that's a polynomial. 1/2 x to the 4th or x to the 4th divided by 2. That's also a polynomial. Okay, the last one, square root of x divided by x squared plus 3. We've got a radical function in the top and a polynomial in the bottom. That's not an exponential function. Okay, and if you want to look in your book, I think there's more examples on page 262 of what is exponential and what isn't. All right, so let's take a look at the graph. Okay, as somebody said earlier, they do grow very quickly. Okay, imagine just letting x be, 6. Okay, that's not a very big number. But 3 to the 6th power, it's getting pretty big, pretty quickly. All right, so let's look at the graphs. Okay, and let's go back to function. All right, so we have 2 to the x. And what I'm going to do, because I don't want to shade above or below, so if yours is set to shade, I think if we just clear that, or you know what, we'll just set it back on line. Okay, and let's graph 3 to the x. Let's start out with a standard window. So there's 2 to the x, and 3 to the x is going to come in right after it. Okay, what do you notice about these graphs as you head further and further to the left? What does that look like is happening? It looks like it's happening, but it's not really happening.
They become closer and closer to the x equals 0.
Closer and closer to which line?
The x-axis.
Closer and closer to the x-axis or the line y equals 0. Yeah. If you go ahead and look at your table, type in 0, they're both 1. 2 to the 0 power is 1. 3 to the 0 power is 1. But then as you start to get more and more negative, you can see they're getting smaller and smaller. And eventually, if you type in a big enough number, the calculator might, actually it's not saying 0, it's saying 0.00 48 times, and then a 1. It's pretty small. All right? And then once they get after 1, both of these graphs really start to take off quickly. All right? So in terms of your domain here, it is negative infinity to infinity. They're continuous functions. The range, though, goes from 0 to infinity, and it will never reach 0. Okay? Never reaches 0. Okay, so sometimes they're going to give us a problem that has a negative exponent in it. What we like to do is try to get rid of it so that we can just look at it as a positive exponent problem. Okay, so let's look at this one. We already know from Algebra 1 that you can take something that's raised to a negative power and you flip it. Okay, by putting the power in the bottom, makes it positive. Anybody think how I can rewrite a to the negative x? And somehow I want to involve a to the negative 1. So I'm thinking the rule I want to use here is a power to a power, so that when I write it that way, I'd be equivalent to the original. And I want to have this in there somewhere. Yeah?
Well, would you start by putting x over a?
By putting x... Well, the a and the x are stuck together.
Would it be 1 over ax?
Yeah, you could write it that way, 1 over a to the x. Okay, or you could think of it as that, and we'll see in a second this is going to be very similar. Okay, because I have a power to a power. If I multiply my exponents, negative 1 times x, I get negative x. And now, using the rule I just had before, a to the negative 1 is the same as 1 over a. So technically, you could write this as 1 over a to the x. But usually we'll put it this way.
So when you have that, you have to distribute your exponent to both terms. So it would just be 1 to the x power over a to the x power. And because 1 to any power is 1, it doesn't matter, right?
Yeah. Yep. So the numerator gets raised to the power and the denominator. So it could be written as 1 over a to the x. But we'll usually leave it like this. Okay. So now we have a trick. If you ever have a base raised to a negative variable, all you have to do is take your base, put 1 over it, flip it, and then you can make your exponent positive. Any question how we did that? So let's compare two graphs. One that has a positive exponent. Okay, we graphed 2 to the x. Let's graph 2 to the negative x. What do you think the negative is going to do? Think about what a negative in front of an x does on pretty much any kind of function. It causes it to do a certain kind of transformation. Yeah?
It's going to flip it?
Yeah, it's going to cause it to flip. Okay, so let's graph 2 to the x and 2 to the negative x. So there's 2 to the x. And there's 2 to the negative x. So it does cause it to flip. In this case, because we're putting the negative right next to the variable, that causes it to flip over the y-axis. If I wanted to flip it over the x-axis, I could put the negative in front of the 2, and that would cause it to flip over that axis. All right, so let's look at the domain and range. Okay, let's start with f of x. Okay, so f of x was 2 to the x. And that was the function in, I think that one was blue. Yep. What's the domain of the function in blue? About Michael?
Sorry, can you repeat the question? I cannot.
What's the domain of the function in blue?
Negative infinity to infinity?
Yep, that's negative infinity to infinity. And how about the range? Sylvia, what's the range of the function in blue?
Wouldn't it be the same?
So you're saying that that function goes up and down forever? I don't think it's going down forever.
Oh, it's going up there.
Yep, so it does go up. Is there a lower limit?
Wouldn't it be 0?
Yeah, it approaches 0 and never reaches it. Okay, and g of x, well, let's take a look at that one. That is going left and right forever. So that one's still negative infinity to infinity. And the range, that's also the same. It's going from 0 to infinity. Okay, so flipping it that way didn't affect the domain or range. Okay, if we flipped it over the x-axis, that would affect the range only. It would now go from 0 to negative infinity. Okay. So using that chart we just had, now we can kind of answer these questions. So as x is approaching infinity, okay, in f of x, what happens to y? As x gets bigger and bigger? About Nick, what's happening to y?
It's approaching 0.
So if we're looking at, let's see, f of x, as x gets bigger, y gets bigger, right? So as x is heading towards positive infinity, so is y. Think of how that graph looks. X gets bigger, y gets bigger. Okay. How about in this graph, as x heads towards negative infinity? What does y approach this time? Yep.
0?
Yep, it approaches 0. All right, so that's for f of x. Okay, now let's look at g of x. So g of x is the one where the graph is kind of flipped around. What happens as x gets really big in g of x? As x starts to get bigger and bigger and bigger, think about what that graph was approaching. Yep.
Or actually 0.
Yeah, 0. G of x is the one that looked like that. Okay, so this time it's approaching 0. And then as g of x, if this x heads towards negative infinity, so does y. Right? So the behavior kind of, it switches around, but it's similar. Any questions on that? So it's important to kind of understand what's happening in an exponential function as x gets really big on the positive side, or it gets really big on the negative side. That's especially important when we're trying to understand whether something is going to grow exponentially or decay exponentially. So the key difference between those two functions, right, f of x and g of x. So this is g of x, but we could think of it as this. It's the same thing. Talked about if you want to get rid of that negative exponent, just flip your base. Here the base is 2. In g of x, the base was 1/2. And 1 is kind of the division point that's going to change whether things are going to start growing really fast or decaying really fast. So if your base is bigger than 1, you have exponential growth. If your base is between 0 and 1, you have exponential decay. Okay, also, we said earlier that those two functions were kind of mirror images of each other. They just looked like they were. But if we actually wanted to prove that they are mirror images, what you have to do is take one of your functions and replace all the x's with negative x's. And watch what happens. Okay, so f of x let's just let that be a to the x. If you replace all the x's with negative, let's watch what happens. Okay. Change the x to a negative, you get a to the negative x. And then to get rid of negative, what do you do with the base?
Put it under 1.
Yep, put it under 1, you flip it. And look at what you get. This is g of x. Now let's do the same thing. Take g of x and replace all the x's with negatives. So instead of 1 over a to the x, I kind of skipped a step, but let me show it to you. Okay, in g of x, you're replacing all your x's with negatives. And that negative is going to cause the base to flip again. Okay? Take your base and flip it. And by flipping it, you can change your exponent to a positive. But what is a to the x? What function is that? That's f of x. So the important point to look at is this equals that. And this equals that. F of negative x equals g of x, and g of negative x equals f of x. If you can take two functions, replace the x's with negatives, and get the other one, that proves that they are reflections of each other over the y-axis. Okay, that won't always work if you take just two random functions. F of x equals 2x plus 3, and g of x equals negative 8x plus 6. I guarantee if you change your x's to all negatives in f of x, you won't get g of x. And the reason is, these are not reflections of each other. Any question on that idea, how to show something is a reflection? Just change all your x's to negative x's and see if you get the other function. That's the basic idea. So luckily, all the transformations you already know work exactly the same. Horizontal ones always do the opposite of what you would think. Plus is going to shift left, minus shifts right. And everything else we already learned. It's all the same. Okay, so without really going into any more explanation than that, let's see if we can figure out how you would transform f of x into g of x. See if we can figure out what all those numbers are going to do. How many transformations are we doing on f of x to get g of x? Yeah, there's 3. 3 different transformations. Anyone think they see the first transformation you would do? And you do them in the same order we've learned all along. Yep.
Shift left.
Yep, how many?
1.
1, yep. So shift left, 1. Okay, anything that's up on the exponent, that's all the horizontal stuff. That's the stuff that's inside. Okay, just like when it's under a root, that's the stuff that's inside the root. Oh, this is what's inside the parentheses. Okay, if you had a number in front of the x, that would be a horizontal stretch or compression. And it could also do a reflection over the y-axis. We just saw that. Okay, but this time we're not having any reflections, no horizontal stretch or compression. What about the 2? Yep, that's a vertical stretch by a factor of 2. So it's going to take all your y values and double the heights. So vertical stretch by factor of 2. What would happen if that 2 was a negative? It would reflect over the x-axis. Okay, the 2, that does your vertical stretching and reflections over the x-axis. And lastly, the third thing is that minus 5 at the end. What's the minus 5 going to do? Sylvia?
Doesn't it shift down?
Yep, shift down 5. Those are the 3 transformations you'd have to do to f of x to get g of x. That's it. Any questions on the transformations? So the next one they want us to do is show that these 2 functions are really identical. And they are. They are the same thing. They look very different. But it's important if you're given 2 things that look different to figure out if they really are the same. Okay? Where that might come in handy is on the test if you get a certain answer and it doesn't match my answer if it's a multiple choice. We might have the same answer, but yours is written differently. Okay? I'm going to start off with f of x. You can take either one of these and try to change it into the other. I think it's easier to start with f of x. You might see one thing we could do to try to start to make this function just look a little bit more like that one. I think there's one thing we should do in the exponent, first of all, because we kind of have different orders here. Yeah, so how would you rewrite that so the 3 comes after the negative 2x?
Negative 2x plus 3.
Yeah. Okay, now at least we get the variable that before the constant. Okay. What's the coefficient of x in the function g of x? Yep. 1. Positive 1. What's the coefficient of x in our function? Negative 2. They're not the same. So what we could do is, let's factor out a negative 2. Just from the exponent. What would that leave me with for a constant now? I mean, a coefficient on x. Yeah?
X minus 1.5.
Yeah, we'd have x minus 1.5. Okay, so the coefficient now here is 1. Okay, but how can so the exponent is starting to match, but I still have to get 0.25 somehow. How do we get a 0.25 out of that? Yeah?
Can you divide by 4?
Well, why? Well, how is there going to be a 4 that ends up in a denominator? That will happen, but, and it's a rule we actually went over when you have a base raised to a negative power. Yep?
2 to the negative second is 0.25.
Yep, and what's the rule to fix, like when you have a base with a negative exponent? What do you actually end up doing?
You're square rooting.
Not square rooting, but we're moving something, yeah. Yeah, you flip it. Okay, when you have a base with a negative exponent, if you want to fix that negative exponent, you flip your base. Okay? Think of your base as this, flip it, and then it goes to the bottom. And then all of that is to the x minus 1.5. And now we basically got it. 1 over 2 squared, that's 1 over 4. And 1 over 4 is 0.25. Okay, so that's how you can transform f of x into g of x. Any question on that? Yep.
So you're basically treating the exponent as if it was its own little expression.
Yep, that's what we did here. We just factored out, we factored out something out of it. You can do anything you want to that exponent as long as it's, a legitimate math operation. Factoring, all that kind of stuff. Yep. Okay, let's take a look at this function. Okay, this is kind of a weird function to think about, okay? Because you're taking a fraction inside. As x gets really big, 1 divided by x gets really small. So you're taking 1, and you're adding something that's approaching 0. But then you're taking that and raising it to an infinitely large power. And so let's see what happens when we graph that. So you get 1, put it in parentheses. 1 plus 1 divided by x to the x. I'm going to start with a standard window. Now x can't be 0 because there's an undefined value there. But x can be anything other than 0. Okay. This graph looks like it's really flattening out pretty quick. Okay, left and right. Go to your table, type in 10. You get about 2.59. Okay, you try a couple hundred, you get 2.71. Let's try 5,000. Okay, 2.718. Let's go to 50,000. 2.7183. It didn't change that much. If you go negative 50,000, pretty close, 2.7183. Anybody ever seen that number before, 2.718? Okay, that's a special number we're going to talk more about. 2.718. It looks like it repeats 1828 and 1828, but then it changes after that. So it doesn't keep repeating in those numbers.
Wasn't that in Mr. Brad's problem video?
E? Yes, there was an E. Yep. So basically, this function looks like it has a horizontal asymptote at, okay, I only went to 50,000, but it was close to 2.718. I think it was rounded to a 3. But this is actually the horizontal asymptote it's approaching. And that number is known as e. Okay, not used quite as much as pi in high school math, but e is an important number when we start talking about logarithms, which is our last couple sections in chapter 5. Okay, so for now, I'm not really going to talk any more about logarithms. It's just that this is a special exponential function. And because we're talking about exponential functions, that's where it fits in. The idea that it has something to do with a natural logarithm, we'll look at that more on probably Thursday. And most calculators have a button for e. Okay, on mine and most other graphing calculators, that the TI-82s and 3s, it's right by the division sign, and you have to press second to get to it. Okay, but that's all I'm going to say about e for now. Any question on that? So let's look at an example of exponential growth. Okay, I said earlier that sometimes if you have a city and the population is increasing at a constant rate, constant percent, that's exponential growth. So let's say at year 0, the population of this city was population of P. Now at year 1, if that's going to increase, let's say it's going to increase by r. What do you have to do before you can even increase something? You have to know what? If you want to increase the price of something from last year, before you can increase the price from last year, you have to actually know what the price was last year. Okay? So to increase the population in year 1, first we have to start out with what it was before, plus we're going to add the increase. Okay? How would you increase P by R? What would you do if R was a percent? What would you do with the P and the R? You do P times R, okay? Which would basically give you that. So let's say you had a population of 100 and it was increasing at 2%. Well, the first year you had your population of 100 plus 100 times 2% is 2. And then 100 plus 2 would give me 102 people. And now the next year, what's our new population that we're starting out with in year 2? It's not P anymore. What's our initial population for year 2? Yeah? Yep. So that's your initial amount, and then you're going to increase that amount by R. Okay, and if you simplify that, it turns out you basically can factor a P times 1 plus R out. So you can write the P times 1 plus R on the outside. If you factor it out of the first expression, you're just left with a 1. If you factor it out of the second expression, you're just left with an R. And what happens is you get P times 1 plus R to the second power. Notice the year and the power match. And this pattern will continue.
So you basically take your original P 1 plus R and raise it to the power, which would be the year?
Yes. So you take P, which is your initial amount, times 1 plus R, where R is your rate, and T, well, that's how many years have gone by. Okay, that's your exponential growth formula. One thing is make sure your rate of increase is a decimal. So if it's 2%, you need to write it as 0.02. What do you think would change in this formula for decay? There's only one thing that would change. Everything else would stay exactly the same. Yeah? Yeah, the plus sign would change to a a minus sign. So let's say you had a 2% decrease. That would be 1 minus 0.02. Or each year, you only have 98% left of what you started with. Okay, so that's exponential decay. The R, the P, and the T all mean the same thing as up above. And since your rate is always between 0 and 1 as a decimal, okay, when you have a minus sign in there, this causes your base of your exponential to be less than 1. And we said earlier, if the base is less than 1, it starts to decrease. If you put a plus sign in there, you're going to get a base more than 1. And that's when it grows. Okay, so this example has a town with a population of 50,000. It's going up at 2.5% per year. Let's model it with a function. So let's find the population as a function of time. And then we'll graph it and find out how many years will it take for this town to reach 100,000 people. Okay, so start out with your initial amount. Okay, what's my initial population in this problem? Well, that's our goal. We want to know when it's going to hit 100,000, but it doesn't start at 100,000. 50,000. The town has a population of 50,000. Multiply that by 1 plus R. What's 2.5% as a decimal? Yeah? 0.25. Yeah, 0.025 to the t. The only thing we could do here is, why don't we write it as 50,000 times 1.025 to the t. There's our model for the population. Now, what do they want to know when the population is going to hit what? Well, listen. 100,000. So basically, we want to solve this equation. Now, right now, we don't know how to do this algebraically. The reason is there's a variable in the exponent. It's very easy to solve algebraically if you use a logarithm. Okay, so we're going to come back to doing this problem again algebraically later on. Okay, but for this problem, they asked us to do it graphically. So what you're going to do is type in 100,000 into one of the two functions. Type 50,000 times 1.025, and you got to use x. We can't use t for the variable here. For my window, the population is only growing, and in fact, it's starting at a minimum of 50,000 people. It's never going to go below that. Oh no, those are years. Sorry. Let's just put 50 years worth of data. That might not be enough, but we'll see. So 0 to 50. And now my population, it can't go below 50,000. And we want to know when it hits 100,000, so maybe put it at like 110, just so it's not on the edge of the screen. Okay, you know, let's set the years a little higher so we don't have to do it twice. Let's try 70 years. Okay, if that's not enough time, we'll have to come back. Okay, so there's the line I want to hit. That was more than enough time. Calculate your intersect. And basically a little after 28 years. Okay, so it's going to take about 28 years for this population to hit 100,000. Okay, so for now, that's how we'll solve an exponential growth problem. Okay, when you graph it, be careful, like I just did, about whether or not you include negatives. Negatives might not make sense in terms of people or time. So, as always, be careful with how you set your x min and x max. Okay, let's look at, we'll do one more growth and then try to finish up with a decay problem. Okay, the growth problem we're going to look at is a bacteria doubling every hour. Time 0 represents an initial amount. Okay, so let's say before it started doubling, you had 100. How many bacteria would you have after the first hour if it's doubling? Yeah, 200. And I want you to think of 200 like this. Think of it as how much you started with times 2. How much bacteria would you have after 2 hours? Orlando?
400.
400. And again, I want you to think of it as how much you started with times 2 to the second power. Okay, after the third hour, you'd have 800. Think of that as how much you started with times 2, because it's doubling, to the third power. So that exponent is basically how many hours have gone by. So after t hours, anybody think they could give me the formula? And it's pretty much what we have here, except we're not having a specific number. We have a variable for the time.
100 times 2 to the x.
Yeah, in this case we use t, but yep, it's 100 times 2 to the t. So in general, the formula for something doubling is how much you started with times 2 to the power of t divided by the length of time to double. So let's say this bacteria wasn't doubling every hour, but it was doubling every 5 hours. Well, then that means only when you hit an exponent of, let's see, if you didn't have divided by the length of time to double, it wouldn't work out right if it was every 5 hours.
So because the length of time to double is every hour, you're
Yeah.
dividing t by 1.
It's like we were dividing by 1.
It doesn't really matter.
Yep. So if it was every 5 hours, you would want the exponent to be a 1 after 5 hours. So if you put in divide by 5, that'll do it. You'd want the exponent to be a 2 after 10 hours. So that's why if you divide 10 by 5, that would give you a 2. Okay, so if it's a 1, you don't have to worry about it. Okay, so it says suppose we have 100 bacteria, doubles every hour, same problem we just had. When will there be 350,000 bacteria? Let's just start by writing our bacteria as a function of time. Okay, what's going to be my formula here to represent how much bacteria I'll have at a given time? Yeah, Andrew, you think you know?
Would be 350,000 is equal to 100 times 2 to the t.
Yep, I'm going to start off with what you said just in the second part. So there's your equation that models how much bacteria there are. And now he already filled in the 350,000 times 2 to the t. And all you do here is graph and then calculate and intersect. And it would be the x value that you're looking for. Just like we did on the last problem. Any question about how you deal with something doubling? What do you think would change for tripling? Yeah?
2 would change to a 3.
2 would change to a 3. So the last one is going to be using pretty much the same formula, except we're going to talk about something getting smaller and smaller. Okay, the half-life. So basically the idea of a half-life is it's the amount of time it takes for half of a radioactive substance to disappear. So let's say you started with, I don't know, 80 grams of something that was radioactive, and it had a half-life of 1 hour. After 1 hour, you'd only have 40 grams left. After 2 hours, you'd have 20. After 3 hours, you'd have 10. Notice the amount gets smaller and smaller and smaller, but it never hits what value? Yeah. 0. It never really goes away completely, which is part of the problem with radioactive waste. It keeps getting smaller and smaller and smaller, but there's always a little bit left. Eventually, it's negligible, but it never completely goes away. Okay, so your half-life formula, you just take your initial amount times 1/2 to the t divided by length of the half-life. Okay, so our last problem we'll look at, we've got a substance that has a half-life of 20 days, and we're starting out with 5 grams. Now 20 days is a pretty quick half-life. Some radioactive substances have half-lives of thousands of years, which is the problem. If it's going to take something thousands of years to kind of start to break down and not be harmful, that's a very long time.